Good morning, everybody. Thank you for being here. It's an immense pleasure for me to welcome you to this special colloquium inserted in the webinar series of the Graduate Program in Physics of the Federal University of Pará in Amazonia, Brazil. I ask everyone to kindly leave the microphone and the camera turned off, except for the moment you are going to speak. Questions will be allowed in the end, unless otherwise requested by the speaker. The questions can be asked using the chat. Today, we'll have the honor to listen to Professor Anthony James Leggett, who was awarded with the 2003 Nobel Prize in Physics, together with Alexei Abrikosov and Vitaly Ginzburg, for their pioneer contributions to the theory of superconductors and superfluids. Our special guest is the John D. and Catherine T. MacArthur Professor and Professor of Physics Emeritus at the University of Illinois in the United States of America. Professor Sir Tony Leggett was knighted Order of the British Empire for service to physics by Queen Elizabeth II in 2005. Apart from the Nobel Prize in Physics, Professor Leggett research on condensed matter physics has been honored with the Wolf Foundation Prize in 2002-03, the Eugene Feinberg Memorial Medal in 1999, the Paul Dirac Medal and Prize in 1991, as well as the Maxwell Medal and Prize in 1975, both of the British Institute of Physics, and numerous other awards. He has been elected to the National Academy of Science of the United States, as well as the British Royal Society and other academics. The question, why can't time run backwards, is what Professor Leggett will answer us today, and I should not make you wait longer to listen to him. Professor Leggett, thank you again very much for having accepted our invitation. The audience is yours.
Thank you. Thank you, Dr. Crispino. It's a pleasure to be able to address you in Brazil. One of the most universal and all-pervasive aspects of our experience of the physical world is that we seem to be able to remember the past and affect the future, but not vice versa. How nice it would be if I could go back to that party the other night and correct that awful social gaffe that I made. But I know that I can't. How nice it would be if I could go forward in time to tomorrow's horse race, find out the winner and place my bets accordingly. But again, I know I can't. So this consciousness that we can remember the past and affect the future, but not the other way around, that seems to be a very, very universal feature of our experience, so universal that we rarely bother to think about it. A somewhat related but not identical point is that if I show you a movie of some simple household process or whatever, then very likely you're going to be able to tell whether that movie was run backwards or forwards. Now, why is this a problem for physics? Well, the problem is that with one very small exception, which most people, I think, feel is not really relevant to this discussion, the basic laws of physics seem not to identify a direction of time. They do not pick out the direction forward in time versus the backward one. Let's just take a quick look at that. Next slide, please. Thank you. Let's first of all just think about Newton's laws of motion, the basic equations of classical physics, classical mechanics. of Newton's three laws, the first law simply says that a body remains at rest or in uniform motion unless it is being acted on by an external force. That says nothing about the direction of time. Newton's third law says that every action is accompanied by an equal and opposite reaction. Again, no mention of the direction of time. So if there is any mention, it has to come in through the second law. Well, Newton's second law says that force is mass times acceleration. The force you're talking about perhaps might be due to gravity or a spring or something like that. Makes no reference to the direction of time. Again, mass clearly does not make any reference. So if there is any reference to the direction of time, it has to be through the idea of acceleration. Now, acceleration is the rate of change of the velocity. What happens if we reverse the direction of time? Well, let's imagine the following thought experiment, where you're standing on the edge of a merry-go-round. And the merry-go-round is rotating clockwise, as in the left-hand diagram. And you'll actually feel a force on your back from the wall of the merry-go-round. That's because you are being continuously accelerated in the direction of the center of the merry-go-round. Now, what happens if we reverse the direction of time? In that case, the merry-go-round will appear to be rotating counterclockwise, but nevertheless, you will still feel a force on your back because you're still accelerating towards the center. So, in other words, when we reverse the direction of time, the velocity is reversed, but the acceleration is unchanged. So that means that Newton's three laws work just as well backwards as forwards. Well, so far so good, but you might ask, what about magnetic fields? It turns out that if I have a magnetic field in the vertical direction, say, and I have a charged particle like an electron, it will appear to rotate, let us say, clockwise around the magnetic field. If I reverse the direction of time, well, you might think the electron will appear to be circulating anticlockwise. There's a snag here. Where does the magnetic field come from? It comes from the existence of currents. And if I reverse the direction of time, then I have to reverse the direction of the currents, and therefore the magnetic field is now no longer up but down, and indeed the electron will be rotating counterclockwise, but that doesn't tell us whether we're seeing the movie forward or backward. So again, that doesn't work either. Finally, you might ask, well, what about quantum mechanics? Doesn't that define a direction of time? Don't we normally start by preparing a system in a given state and then later on let the system evolve and later on measure it? And doesn't that involve some idea of the direction of time? Well, that's a slightly more complicated issue, but people have thought about it a lot. And the conclusion is no. It's perfectly possible to formulate quantum mechanics in a way which is totally time symmetric. There's nothing about time flowing forwards or backwards. Let's just look for a moment at a slightly different, although related point. Next slide, please. Thank you. Here is a typical textbook problem in elementary mechanics. We have a cannon, that's the blue object in the picture, which is firing a cannonball, the red object. And typically, the textbook will tell you the initial position of the cannonball and its initial velocity. And you're supposed to know that gravity is acting on the cannonball. And the textbook will ask you to calculate the trajectory of the cannonball, and in particular, it'll ask you to calculate the final position and velocity. Right? It's a straightforward calculation. So it looks as if then, if we know the initial position and velocity, we can determine the exact trajectory and the final position and velocity. So it's very tempting to think then that the initial conditions are causing the subsequent motion. And this idea is the basis of a famous thought experiment due to the famous French mathematician and physicist Pierre-Simon Laplace in the early 19th century. Laplace said, suppose we consider a demon whose faculties are so acute that he can actually know the position and velocity of every body in the universe. And he takes it for granted that the demon also knows all the forces acting on these particles. And he says that this demon would then be able to predict the complete subsequent behavior of the universe, including presumably of human beings. And although Laplace himself did not draw this conclusion, the conclusion which is drawn by many people from that thought experiment is that the idea of human free will is an illusion. I just raised my arm. I thought I did it by exercising my free will. But no, people say, that's not right, because the actions of your arm and the actions of everything in the universe are totally determined within Newtonian mechanics by the position and velocity of all the particles at some previous time. So at first sight, that looks like a tempting argument. However, there's a snag. Technically, Newton's laws are actually second order in time. And what that means is that any two independent pieces of information are sufficient to determine the complete trajectory. So in the case of the cannonball, we could simply ask what is the final position and velocity, and from that we could work backwards to determine the initial position and velocity. In other words, the final conditions could be regarded as causing the initial conditions. And there are many other possibilities besides that, which I needn't go into. But the point is that there is no basis in Newtonian mechanics to the idea that the past causes the future rather than vice versa. Next slide, please. Well, this state of affairs worried people a lot in the early 19th century. And there was a group of very brilliant physicists and engineers who figured out a possible solution. And the solution goes something like this. Imagine that we have a system of many, many particles, not just one particle now, but many particles, contained in a container which is partitioned. So with a partition which can be withdrawn. So suppose initially this body of particles, a gas, say, this gas of atoms, suppose this gas is confined entirely on the left-hand side of the container, with the partition, of course, still in place. At some time, then we imagine that we withdraw the partition so that the gas can now expand into the whole container. Now, once it's done that, we know that unless we take a drastic hand in the matter ourselves, those atoms are never going to spontaneously reassemble so that they're all back on the left-hand side. So in other words, the state in the upper diagram can evolve, given appropriate conditions, to the state in the lower diagram, but never vice versa. Why not? Well, it's basically a matter of the number of states or the available space available. Next slide, please. Yeah. Let me illustrate this with an analogy which I can always use safely when I'm talking to an audience in the US, because everyone in the US at the university stage has certainly undergone a course of driver education. Now, I'm not sure if all of you have, but I think you can sort of imagine what would happen if you did. So imagine that you're taking a driving lesson and the driving instructor takes you to the driving school car, which is parked by the sidewalk. And he instructs you, you get in the driver's seat, and he instructs you to drive out into the road. Well, generally speaking, you don't have a great deal of difficulty doing that. On the other hand, at the end of the lesson, you come back to the position you left originally, and he asks you to go and park in that space. And anyone who's actually ever taken a driving lesson will know that this is very much more difficult. Why so? Well, it's in some sense rather commonsensical. When you drove out of the parking space into the road, it didn't really matter exactly where in the road you went. There's lots and lots of possibilities, lots of space available. When you come back, on the other hand, you have to get into that very precise space. So the number of possibilities available is much, much smaller. So this led more generally to the idea of disorder as a physical quantity. And this was defined by these early 19th century thinkers as being proportional not to the available space itself or the number of available states. That turns out to be inconvenient in practice. It's more convenient to define the disorder as proportional to the logarithm of that quantity. And then you define a physical quantity, which is called the entropy, and usually denoted S, as a measure of the disorder. And there is a famous equation which is associated with the name of Ludwig Boltzmann, which says that the entropy, S, is a particular constant times the logarithm of the number of available states. And so now it begins to get rather plausible that the number of available states can only increase in time. It can't spontaneously decrease. And therefore, that the entropy should only be able to increase in time. So this leads to the famous second law of thermodynamics, which basically says that for a closed system, a closed isolated system, the entropy can only increase with time, or at best stay constant, can never decrease. And many textbooks take you through this argument, and basically they stop at this point and say, well, obviously that is the origin of time asymmetry. The direction of time is the direction in which entropy is increasing, and that's the end of the story. But wait a moment. Let's do a little thought experiment. Next slide, please. Thank you. Let's imagine, I imagine most of you are used to the idea of shuffling a deck of cards, playing cards. But we're not going to do it by hand. We're going to do it by a machine. So we built ourselves a machine whose function is to shuffle decks of playing cards. And we put it in a locked and sealed room. And in this room, there will be a camera which can actually take a photograph of the arrangement of the deck of playing cards after any particular shuffling event. So imagine that we start off from a rather nicely ordered deck. I expect most of you will recognize that this first column in the figure is rather nicely specially ordered: ace of spades, king of spades, queen of spades, jack of spades, etc. So now imagine that we turn on the machine. It will start shuffling the cards, and as a result, the subsequent arrangements of the deck of cards will become more and more disordered with time. So in other words, this is a good example of the idea that disorder is going to increase with time. But wait a moment. Suppose that we were to come into the room at, say, midday, 12 o'clock, and look at what the camera is showing, and the camera is showing this first column: ace, king, queen, jack of spades, etc., etc. Well, of course, our first thought would be that someone must have somehow snuck into the room and arranged the cards in that way. But we can just check the previous shots taken by the camera, and we can convince ourselves that that is not so. So, however, we still know that at 12 o'clock exactly, we had this very, very nicely ordered arrangement. Now I ask the question, what happens if we go back in time? After all, the machine was shuffling before 12 o'clock, and the inverse of a shuffling process is itself a shuffling process. So if we go backwards in time from 12 o'clock, we have to imagine that in that direction also the disorder would increase. Or putting in other words, before 12 o'clock, the degree of order was increasing in time. So we wouldn't normally draw that conclusion. Well, at first sight, is that the reason is you might think, is associated with the fact that we take for granted that as human beings, we can prepare a given arrangement, like the perfectly ordered deck of cards. We can prepare it and let it run forward in time, but we can't retro-prepare the system and let it run backwards in time. So at first sight, you might think that the arrow of time has to do with what we as human beings can and can't do. But that actually can't quite be right, for the reason I show on the next slide. Next slide, please. Okay, imagine that we have a rock which is perched rather unstably at the top of a cliff. After some time, erosion takes place, the rock becomes detached and falls downwards down the cliff and into the lake at the bottom. And as it falls into the lake, it'll generate waves which radiate outwards to infinity. And eventually the rock will settle on the bottom of the pool. Now imagine that we played that movie backwards. So the rock would appear to rise spontaneously from the bottom of the pool. The waves would come in and converge towards the point at which the rock appears. The rock would then spontaneously move up the cliff and reattach itself at the top. And we know for sure that then the movie is being run backwards, despite the fact that there are no human beings inside here. So how do we explain this curious asymmetry with respect to time? Well, as I say, people in the early 19th century worried a great deal about this. And one person who worried a lot is Boltzmann. Next slide, please. Yeah, here is Ludwig Boltzmann. Here is his grave in the Zentralfriedhof in Vienna. And perhaps you can see, I'm not quite sure if it's visible, but you can see that above his head is the inscription of this famous equation, S equals K log W, which is slightly ironical because according to the historians who've actually studied these things seriously, there's no evidence that Boltzmann himself actually ever wrote down that equation. Certainly it comes from his ideas, but we have no record of him ever actually having written it. Anyway, as I say, Boltzmann got very worried, and he came up with a really very interesting possible solution to the problem, which actually ahead of its time by something like 150 years. Next slide, please. Okay, so this is roughly how Boltzmann's solution goes. He says to himself, well, look, the natural state of the universe is to be as disordered as possible. And in some sense, when left to itself, the universe will tend to be in a state of maximum disorder, so S sub max. However, we do know from statistical mechanics, which is an area to which Boltzmann contributed very, very substantially, we do know that from time to time, there will be small fluctuations away from this state of maximum disorder or maximum entropy. Now, these are very improbable fluctuations and they only take place very locally, but they will happen. And then once the fluctuation has occurred, it will tend to restore itself. The system will tend to go back, as on the right-hand side of the curve, to the state of maximum disorder. Now, suppose that we happen to be living at a point on that curve marked by the black dot. Then we will see the degree of disorder and therefore the entropy increasing towards the right. And therefore we will identify the direction towards the right as the future. Suppose on the other hand, we'd been sitting on the left-hand side of that dip. Then we would see disorder increasing towards the left, and that is the direction which we'd identify as the future. Well, so far, so good. But then Boltzmann raised the question, yes, but wait a moment. How come that we are actually sitting in the middle of this very improbable fluctuation? After all, the odds are that if we just pick a random point anywhere in the universe, then the disorder is going to be a maximum. So this argument would not work. And he came up with essentially an anticipation by 150 years of the so-called Anthropic Principle. He said, well, if we were to find ourselves in this sort of random position in the universe, where the entropy is maximum, then, crudely speaking, the physics as we know it would not work. Certainly, chemistry and biology would not work, and we would just not be there to ask the question. In other words, the reason that the current state of the universe is what it is because if it was something very different, we would not be here at all to talk about it. And as I say, that's really an anticipation of an idea which has got much prominence in cosmology and particle physics in recent years, which is that if the state of the universe and the various fundamental constants and so forth were different by only a very slight amount, what they are, then human life would not be possible. We would not be here to ask the question. Well, that works okay as far as it goes, but this is plausible perhaps in Boltzmann's time because it could be reasonably claimed that our particular neighborhood in the universe is very untypical of the universe as a whole. But alas, nowadays we have satellites and space telescopes and so forth, and we can actually check that we're not living at all in a specially privileged place. As far as we can see to the most distant quasars, the universe is pretty much the same as what it is in our immediate neighborhood. So that, unfortunately, doesn't really seem to work, although it's a very brilliant idea. Well, at this stage, let's try to just review the different so-called errors of time, which people have talked about in the past. Okay, next slide, please. Thank you. Well, the error of time with which I started was the psychological one, namely we can remember the past and affect the future, not vice versa. But this is a bit different from the biological error of time, which says that plants and animals appear to start small, grow bigger, and eventually die. Then there's the electromagnetic error of time. It's, I think, not totally trivial observation that both natural objects like stars and man-made objects like light bulbs emit radiation rather than absorbing it, even though the fundamental laws of electromagnetism allow both equally. Well, then there's the thermodynamic error of time, which we've already talked about, the idea that entropy always increases with time. And finally, there's the cosmological error of time. It appears from our observations that the universe is expanding rather than contracting. So the question arises, are these 5 errors of time actually related? Well, I think it's fairly plausible, at least, that there is a relation between the psychological and biological errors. There's no logical contradiction in the idea that I might be able to remember a time when my hair is even whiter than it is, and I'm having to walk with a stick and so forth. That's I fortunately don't have to now. And I might be able to affect causally the time at which I was howling in my mother's arms. But somehow I think most people will think that may be a logical possibility, but it's not a scientific possibility. There are good reasons why the psychological and biological errors should be identified, even though the details of this are really, at least at the moment, I think not very clear. The relationship between the biological and electromagnetic errors, I think, is rather straightforward. After all, how do plants or animals grow? They basically, in the case of plants, they basically grow by absorbing energy from the sun and turning it into chemical energy, etc., etc. If the sun were not radiating energy but absorbing it, of course that would not work. I think that particular error is rather straightforward. Again, the electromagnetic error is itself only a special case of the thermodynamic error, because it's rather easy to convince oneself that the state in which the radiation has been emitted from the star is much more disordered than the one in which it's still retained by the star, and that you can almost make fairly quantitative. Finally, what about the relationship between the thermodynamic and cosmological errors? That's actually a rather more tricky point. Next slide, please. Yeah. There is a pretty standard model of the universe, the so-called Friedman-Robertson-Walker model, which most cosmologists today believe. And it goes something like this. Whatever the current state of the universe today, if we go backwards in time, it will look as if the universe is getting both denser, that's more closely packed, and also hotter. And eventually we'll come to a point where if we just take out the equations, which we believe literally, then we find that the universe has become, or was, infinitely dense and infinitely hot. And that is what we normally call the hot Big Bang. So I say all FRW type models do predict a hot Big Bang. This is rather closely related to the theoretical work for which Roger Penrose a few days ago got the Nobel Prize. He basically, in effect, showed that this had to happen as you go backwards in time and under other conditions. What happens if you, well, okay, let's just pause for a moment and ask, okay, fine, but in order to make a connection between cosmology and thermodynamics, what we have to assume is that the universe was incredibly well ordered at the hot Big Bang, that is at the end when it was small. And in fact, we do have very substantial experimental evidence for this. It looks as if the universe was very, very much more ordered than it had, as it were, any right to be at the hot Big Bang. And the heavyweights in this field, like Roger Penrose, like the late Stephen Hawking and so forth, argue furiously about whether this is a natural state of affairs or not. In other words, whether it's natural that disorder should be low at the small end. Well, next slide, please. Irrespective of that, I mean, let's agree for that for a moment, but irrespective of that, let's ask the question, what about the future? Now, in fact, there is, could you go back one slide, please, for a moment? Thank you. I'm sorry that part of this, at least for me, is cut off. I hope you can see the bottom of this slide. It turns out the future of the universe actually depends rather strongly on the value of a certain quantity, which is essentially the density, the mass density of the universe expressed in appropriate units. This quantity is usually called capital omega. And there are really three possibilities. Omega could be less than 1, in which case the universe will go on expanding forever. It could be equal to 1. You might think that's very improbable indeed, but it turns out there are some reasons why it might not be that implausible. If omega is exactly equal to 1, then the universe will essentially expand slower and slower and eventually cease to expand at all and just stick at some final value. Finally, if this quantity capital omega is greater than 1, then the universe will expand to a maximum volume and then contract again. So let's go now to the next slide, please. Yep, good. So in this case, then, if the universe is closed, as the technical name for omega being greater than 1, then we will expand to a maximum size and then contract again, and eventually contract to infinite density. And that's what is sometimes called the Big Crunch. Now, an interesting question is, suppose that we were actually on the right-hand side of this curve. First of all, in which direction would the entropy behave? Would it increase or decrease as we go in towards the hot Big Crunch? And an associated question is, just suppose, which seems extraordinarily improbable, let's suppose that there are human beings who still exist at this point in the history of the universe. Which way would they see the future? Would they see it towards the right, towards the hot Big Crunch, or would they see it in the opposite direction, which is certainly the inference we would make on the left-hand side of the curve? And believe it or not, the real heavyweights in cosmology disagree furiously about this point. So I certainly don't want to try to adjudicate it, but just be aware that there is this dilemma. Okay, next slide, please. I think it's the final one, probably. Yep, good, thank you. Well, let's imagine that we are satisfied with the idea that if, in the last resort, the arrow of time, as we are seeing it today in everyday life, does derive eventually from the cosmological asymmetry. In other words, that the entropy was very large, very small at the hot Big Bang and is thereafter continuously increasing. As I say, there are difficulties with this point of view, but let's just pull those aside for a moment and ask a rather different question. Could the arrow of time reverse itself locally and temporarily? Why would anyone think of that as being a plausible possibility? Well, basically, it's because of a famous series of experiments which have been conducted over the last few decades. For those of you who know the name, these are the so-called Epr Bill Experiments. And basically, they go something like this. We have an atomic source which is emitting pairs of particles, in fact, in this case, photons, particles of light. And these photons are directed towards switches at the left-hand end and at the right-hand end. So the photons are emitted back to back. The right-hand photon will eventually get into a switch, which will direct it into one of two measuring stations. And these two measuring stations measure two different properties of the photon. So, for example, measuring station C at the right-hand end might ask the question of the photon: are you polarized horizontally or vertically? Whereas station D might ask the question: are you polarized at 45 degrees this way or 45 degrees this way? These are different questions. You can't ask them both at the same time. The same is true to for the other end of the laboratory where the left photon goes. Now, the raw data in these experiments are quite simply whether you get a click or not in the counters for each pair of photons. So for each pair of photons, you record whether you got, well, of course, you record which counter the photon was switched into, but you also record whether that counter clicked or not. And you do the same for the other measuring station at the other end of the laboratory. And that's your data. Now, it turns out that and crudely speaking, what you're interested in is the correlation between the raw data taken at one end of the laboratory and those taken at the other. And it turns out that the observed correlations, the ones which are observed in real-life experiments, are, well, first of all, they're consistent with quantum mechanics, but that's not what we're really interested in this context. Much more importantly, the data are inconsistent with any theory which embodies three postulates. The first is objectivity, that is the idea that microscopic objects like photons have definite properties whether or not those properties are actually observed. The second postulate is locality, which means that no causal influence can travel faster than the speed of light. And in fact, these in real-life experiments, the two measuring stations are so far apart that nowadays sometimes by as much as 1,000 kilometers, so far apart that there's no possibility of a light signal connecting the events at the two stations. And the third postulate has to do with the arrow of time, the idea that events in the future cannot affect the state in the present. Which of these are we going to throw away? Well, in fact, most practicing physicists tend to throw away the idea of objectivity. This is already present. The notion that objectivity could not be maintained at the level of elementary particles like photons was already there in the very early days of quantum mechanics in Niels Bohr's ideas. However, not everyone likes this, and there is a school of people who would like to keep objectivity. Locality, well, popular writers on this subject tend to throw away locality. But most practicing physicists are very loath to do that because locality is really at the foundations of Einstein's special theory of relativity. And if we throw that away, really the whole theory goes up in flames, which is not good because it is very, very well verified experimentally. So let's look at this final idea, the final ingredient, which is the arrow of time. Could it be that in some sense the arrow of time can be reversed in these experiments, so the initial state of the atoms which emitted the photons was causally affected by the events which took place in the future, that is, by the clicks or not clicks which occurred in the counter? Not quite as ridiculous as it seems. Imagine, for an analogy, think about a ferromagnetic material like iron. When iron or some other ferromagnetic metal is in the ferromagnetic phase, that is below its Curie point, you will find that on average all the spins or all the little magnets associated with the atoms are pointing in a particular direction. Nevertheless, even in that state, it turns out there is a non-zero probability that a small group of spins should be able to reverse themselves and point in the opposite direction to the majority. Now, this is a fluctuation and it will only last for a small time, but it happens. So could it be that analogously, even though, as it were, on average, the arrow of time is running, as we normally understand it, from past to future, nevertheless, there are small regions of space and time, and in particular, they are sometimes activated by this kind of experiment, where the opposite is the case. Well, people have played around with that idea, and it looks as if it's formally possible. You can write down equations which certainly embody this idea, but what is really not, I think, clear is whether you can then embed these small fluctuations in the average universe in which the direction of time is what we normally think it is. Well, I have not, as you see, solved the problem of why time can't run backwards. However, let me just close with the final remark. If we look back on the history of physics for the last 500 years or so, we see that just about every major revolution in the history of physics has involved the overthrow of something which until that time seemed just plain common sense. It was common sense that the sun goes around the Earth until Copernicus told us otherwise. It's common sense that the relative time of two different events was independent of who was looking at it until Einstein told us otherwise. Common sense that elementary particles behave in the same way whether or not we're looking at them, till Heisenberg told us otherwise. So every major revolution has been accompanied with the abandonment of some common sense notion. My strong guess is that if there is another major revolution in physics in the next 100 or 200 years, say, and I'm inclined to think there will be, then that revolution will involve, among other things, a drastic revision of our ideas concerning the fact that the past can cause the future, but not vice versa. If you ask me to try to tell you what such a new theory would be like, the only reply I can give you is one which I'm told was given by the late jazz musician Louis Armstrong to a fan who asked him where jazz was going. And his reply was simply, "Man, if I knew where jazz was going, I would be there already." Thank you.
Okay, Professor Anthony Leggett, thank you very much for your very, very nice talk. And I'll ask everybody to, yes, for a round of applause. Okay, so, thank you very much once again. You see, people were, faster than even I asked for the rounds of applause, because they are very much happy with their wonderful talk. While people are preparing for questions, we have already some questions, but let me give you some information of what, of the audience that has been present during your seminar. So we have more than 100 people counting together the Google Meet room and also the YouTube streaming. And we had people from, representatives from all around Brazil, I would say, from states like Amapá, Pará, Amazonas, Paraíba, Piauí, Pernambuco, São Paulo, Rio de Janeiro, Paraná, Rio Grande do Sul. This means that we have people from the top, the top north of Brazil, which is the Amapá state, to the top bottom of Brazil, right, in the Rio Grande do Sul. So it's an audience representative from all around the country, but not only that. So we had people from abroad, as far as from Netherlands, India, Sweden, Jerusalem, and Portugal, that I have counted. Obviously, I did not have the register of everybody, but obviously we have the representatives of our graduate program, our students, our teachers and professors, as well as from the countryside of the state of Pará. So this is quite a huge opportunity for us, and I'd like to thank you once again for that. So let's start with the questions. So the first question is from Satish Kumar VH, who works in Brazil. Satish, do you want to make the question yourself, or do you want me to read? I'll read it then, okay? So Satish has written, are there CP violating condensed matter systems where the arrow of time can be reversed?
Yeah, that's a rather interesting question. But in fact, one can take that question in two ways. Are the condensed matter systems in which on the macroscopic scale the second law of thermodynamics might appear to be reversed? And the answer to that is, well, yes, in a sense, in the following sense, that if one just cuts out a small subsystem and just studies that over a finite period of time, you may find the odd fluctuation in which the entropy of that system appears to be reversed, and therefore you tend to say that locally the arrow of time is reversed. However, that's not exactly what I was talking about, in fact, when I discussed the last slide, and I don't think that would violate our normal preconceptions. But I suspect that the questioner was actually asking a slightly different question, since he or she did mention CP violation explicitly. There are, as far as I know, there are at present no experiments on condensed matter systems which demonstrate CP violation in the sense in which particle physicists talk about it and have known about it for whatever 50 years now. One can certainly think of possible experiments. I have actually in the past proposed an experiment which would look for, not for CP violation, but simply for P violation in condensed matter systems. And this experiment may, I believe, be done sometime in the next few decades, hopefully. I've also proposed, and other people have proposed, experiments on condensed matter systems which would test for time reversal explicitly. Again, those have not been done at present. They may be done sometime in the not so distant future. I'm not quite clear if I answered the question, but that's the best I think I can do.
Okay, so thank you, Satish, for your question. Thank you very much, Professor Leggett, for your answer. We have one more question kind of related. From Albert Petrov from University of Paraíba in the northeast of Brazil. Albert, do you want to make the question yourself, or do you want me to read it for you?
I will make the question.
Okay, Albert, so go ahead, please.
Well, my question is the following. It is known within the concept of Lorentz symmetry breaking that in some versions the CPT breaking is also suggested as a possibility. So the question is, perhaps the CPT breaking can introduce a solution for error of time, for irreversibility of time.
Yeah, thank you. Very interesting question. Yeah, I think the answer is basically yes. But in other words, what could, I think, eventually turn out to be the case is that if we study the basic equations of cosmology carefully enough, or alternatively, if we perhaps manage to find new equations which control the development of the universe, what we might conceivably find is that the natural solutions to those equations do turn out to spontaneously break the time symmetry of the equations themselves. In that case, either the universe would have to be spontaneously expanding, or it would have to be spontaneously contracting. And of course, if it's doing one or the other, well, not of course, but if it's doing one or the other, then it might turn out that entropy increased in the direction corresponding to that. So I think basically the answer to your question is yes, but the devil is in the details.
Okay, so thank you very much, Albert, for your question. Thank you very much, Professor Tony Leggett, for your answer. So we have some more questions here. I have one question from Parto Majumdar that is listening for you from to you from India. So Parto, do you want to make the question yourself, or do you want me to read it for you?
Can I ask the question? Can you hear me? Professor Leggett, how wonderful to see you and to hear this wonderful talk. Thank you very much indeed. I did write a question down, but could I ask a slightly different question? Since you bring in cosmology, your fellow Nobel laureate of this year, Professor Roger Penrose, has a theory of cosmology which involves the cyclical nature of time. I don't know if you're aware of this construction, but there you have a time sort of going in a circle, and in a very large scale, of course, where you have black holes evaporating, and then they set the creation properties for a future universe, which also has black holes forming and so on and so forth. So I was wondering whether, if you have anything to say about cosmology where you have a cyclic nature of time?
Yeah, okay. Well, I'm most certainly, as I'm sure you can see, I'm most certainly not a professional cosmologist. But my impression is that indeed one can consider models of the kind which Roger Penrose has developed. The only problem is that it seems extraordinarily difficult to obtain any experimental information which would distinguish these from the standard FRW model, where one simply says that, well, you just follow the equations as we know them, backwards in time, and you find that there is simply a point at which they no longer make any sense, a sort of singularity, the hot Big Bang. One can certainly envisage the possibility that in some sense the universe existed before the hot Big Bang, or if in the case of a closed universe that it will exist after the hot Big Crunch. The only problem is how do we actually gain any information from it about this? And this would, I think this would depend on the details of the theory, and I'm afraid I'm not familiar enough with Penrose's detailed arguments on this point to know whether he believes that we could indeed do experiments, at least in principle, which would tell. If we can't do experiments which would distinguish between these different pictures, then I'm somewhat tempted to say, well, then they probably are not really the domain of physics, but of some of the other disciplines, such as say, philosophy. But that's one possible point of view. It's not the only one.
Okay. Thank you very much.
Okay, so thank you very much, Pato. Thank you very much, Professor Leggett. So we have one more question here from Andrei Bagrov. Andrei, would you like to make the question yourself, or would you like me to read it for you? Yes, I'll read it then. So Andrei has written, are you aware of a recent paper on Wigner's friend type experiment, where it has been claimed that if one sticks to the assumptions of locality and free will, then the reality is observer dependent? So he mentions the archive number of the paper, and he asks if you have any opinion about that.
Well, actually, to be honest, it would be more useful to know the authors of the paper.
Okay, so he has not written, but I can try to figure out in a moment. So, well, it's a set of authors that Massimiliano Proietti, Alexander Pixton, Francesco Graffiti, Peter Barrow, Dimitro Kundis, Cyril Bruntyard, Martin Ringbauer, and Alessandro Fedrizzi. So it's a paper from last year, and it's named Experimental Test of Local Observer Independence. Anyway.
Okay. Yes. Okay, now I have to say that I'm not entirely sure whether this was one of the papers that I have read. I know that over the last year, 2 years maybe, there has been a lot of interest in the Wigner's friend paradox, and several papers have appeared on it. I have read some of them, but not necessarily all. So I'm not entirely sure that I have read the one that the questioner is talking about. I have to say that I think the theory which goes into these papers which I have read on this subject is not uncontroversial. That is, some of these papers at least seem to be applying quantum mechanics in a way which at least some people would think is actually not strictly legitimate. Nevertheless, there's some very interesting ideas there. Of course, needless to say, we are currently many, many orders of magnitude away from the conditions which we would need to conduct a meaningful Wigner's-Friend experiment, and some people would claim that there are, as it were, a priori reasons why we will never be able to conduct a Wigner's-Friend experiment. But I think it's one of these areas where simply by posing the question, one is forced to think more about the real meaning of the formulas of quantum mechanics. So I think this kind of discussion is definitely valuable, whether or not we're eventually ever going to be able to do the experiment. So I rather suspect we will not be able to do it, but never mind. So I can't really answer whether I think this particular paper is, whether I believe it or not, because I am not sure that it's one of the ones I've read. But that's my general feeling about the Wigner's-Friend experiments.
Okay, Andre, thank you very much for your question. Thank you, Professor Leggett, for your answer. And we have a question from Professor José Ademir Salles de Lima from University of São Paulo. Ademir, do you want to make the question? Turn on your microphone.
Yes, I may do my question. First of all, I'd like to thank Leggett by the great seminar about the error of time. Now we know that the error of time is a problem involving several interfaces, no? Non-equilibrium thermodynamics, quantum mechanics, quantum field theory, biology, cosmology. And I think that one of the big problems to understand better the error of time is related with the role played by gravity. That points to cosmology. For instance, in the example of the gas that is expanding, the usual example that it's very common to show is that if you cut the partition and then the gas occupy the whole volume and the entropy increases. But this kind of gas is a lab gas where the gravity is neglected.
Yeah.
But if this gas is self-gravitating, and then the tendency of the gas is to aggregate. Even when you cut out. I am thinking a gas in the universe, in the expanding universe, because we have the local gravity. And the problem perhaps is related with the fact that if we have a self-gravitating gas, we may form black holes. And the black holes is a machine to store entropy. Perhaps the major part of the entropy of the universe are in the black holes, not in the cosmic background radiation. And then I don't understand how to catch the role played by gravity in the expansion of the universe. There are two problems here. If you just pay attention to the expansion of the universe, it seems that there is an error of time. If you consider, for instance, a Friedman model or even a lambda CDM model, a model with driven by the vacuum energy density, at the level at the unperturbed level that we call in cosmology the level of the history of the cosmos, there is no error, an error of time. In order to see an error of time, we need to perturb the model. We need to form galaxies, because the unperturbed universe don't form galaxies, and then we need to perturb. And these fluctuations started to aggregate the matter. And we are aggregating, but we are increasing the entropy. And then the role played by gravity, I would like that you comment about that. Because it seems that it's something that we don't understand. Perhaps I am wrong, but it seems that the role of gravity in non-equilibrium thermodynamics is not completely understood.
Okay, thank you. Perhaps I could just, in some sense, reply to your final sentence. I think, indeed, there are many things which we don't understand concerning the applicability or not of general arguments from thermodynamics to the very special situation which is created by the formation of a black hole. And since in some sense you can think of the universe itself as simply a supermassive black hole, then of course this refers also to the to cosmology in more general terms. So I think this is essentially the thrust of your question. I don't myself feel that the current ideas which we have in cosmology are likely to be the final truth. In fact, I think that is that among the different areas of physics, that is probably the one where there is most likely to be a drastic revolution sometime in the next, say, 50 years. Basically what I'm saying is, I don't know, but thank you for raising the question.
Okay.
Thank you.
Thank you, Ademir, for your question. Thank you, Professor Leggett, for your answer. So now I think we come to more or less the time that we have agreed that you would stay with us. So Professor Tony Leggett, thank you very much once again for your wonderful talk and explanations. I'll ask everybody, before we end, everybody to turn on their microphones to a final round of applause.